obtained her PhD in physics in a joint program between Harvard and Alexandria University in Egypt. She carried out most of her PhD research at Lawrence Livermore National Laboratory to develop MED positron beam for channeling an in-flight annihilation experiment. Then she worked as a postdoc researcher at Idaho Accelerator Center. Then as a research assistant a professor in Washington State University. And she's currently an associate professor at Bowling Green State University. Professor Selim has published more than 100 peer-reviewed journal articles. She has 3 patents. She's known for inventing the new positron annihilation spectroscopy technique, which is called the gamma-induced positron spectroscopy. I believe you're going to mention a little bit later.
Yes, probably one slide.
Which has been adopted and used for developing new positron facilities in Dresden, in Germany, in Japan, and in India. She has extended positron application to new areas in material science. And currently, she has active research programs on electronic, photonic materials with a focus on growth and characterization of semiconductors and wide bandgap oxide. But I would add to that structural alloys now because Professor Selim is actually a collaborator of ours on a new project where we look at radiation damage and corrosion in structural alloys for Gen 4 reactors. So she currently serves as an advisor on 3 international committees, the International Advisory Committee of Positron and Positronium Chemistry, the International Advisory Board on Positron Studies of Defects, and the Advisory Committee of the International Conference on Positron Annihilation. So please, let's welcome Professor Selim.
Thank you very much, Gamal. Thank you very much for the invitation and for the nice time here. It was really very nice to visit this campus here. I visited this campus a long time ago, and I'm really glad to see the campus here and everybody. So thank you very much again for hosting me here. And hopefully I don't disappoint you. My background again is physics, so I'll try to get some stuff which is related to nuclear engineering, but most of my work, I'll probably give you a little bit idea about what we, from here. I'll give you a little idea about what we do in our lab, so you know, I'm not really nuclear engineer person, but then I'll tell you where is the intersection between, like I said, physics and material science and the nuclear engineering. So in our lab, very much we're doing, we grow fundamental study and applied research in what we call wide bandgap oxide, but we have also, like Jamal mentioned, we have some interest in structural material and engineering material. So we do synthesis material, we grow nanostructure, we have clean room class 100 in our lab. We have metal organic chemical vapor deposition. We can do epitaxial growth of oxide for semiconductor device and for photonic application. And we do a lot of characterization from electrical transport and measurement to luminescence and optical characterization. And important field of ours, of course, is defect spectroscopy. And for defect spectroscopy, we use positron annihilation spectroscopy as a main technique, and thermal stimulated luminescence and the other optical technique. Positron, probably my focus is going to be here on positron, because I don't know if you guys know, you have a nice positron facility here. I don't know if people are aware of this or not. And then positron has a lot of application, and it has been always one of the interesting techniques to look to nuclear material and to study defective material. So it is really, if you look to the literature, positron has been really useful to look to this kind of study. So my focus is going to be on this part to introduce to you what's positron annihilation as a physicist, what is positron, how positron used to study defects, and then I'll talk a little bit about something else I do, which is related to detectors, nuclear detection stuff. So this is very much is most important, but this is some of the list of experiments set up in our lab. When I go to colloquium, I always show people because they're interested in the use of in our facility. So this is some of the stuff we have in our lab, but you probably see most of them, it's really electronic and photonic stuff. But we have defect spectroscopy, a big part of this. So this is some of our active research project, and my focus, as I said, is going to be radiation-induced. So radiation-induced defect in materials, this is my collaboration with Jamal here. This is what we do with it. We do positron spectroscopy, we do TM, and this is where it's our collaboration. So I'll talk a little bit about that. This is why I'm going to talk about study of defect here. And the other part, the development of scintillation detector, and I think you have some area of here to they do. And I'm going to mention at the end about neutron transmutation doping. So let me start. This is, I already told you the outline of my talk before I show it. So introduction to positron annihilation, defect study, and application of scintillation. So yeah, let me give you a little bit of history about, so I assume nobody but know positron here, right? Except you, yes. So positron is a positive electron. So you know electron, everybody know electron. So simply positron is a negative, is a positive electron. Where it starts, let me start with a little bit of history. So Dirac, if you know Dirac equation in quantum mechanics, so Dirac equation, he actually solved the equation and he got negative energy solution. So he said this is like positive electron. He found a hole with property similar to the electron. So this was just the theory. And then Anderson, he measured actually the positron in 1932. And this is the first image actually for positron detection in a cloud chamber. So this is how start the positron. And this guy get Nobel Prize. The two get Nobel Prize actually for the discovery of positron. And after this, people show that you can use positron to study electronic structure of material, and I'll show you that it's been really one of the very important methods for this. And then established to study defect in 1950s, and then it go to positron emission tomography, also around this area in 1950. So you're familiar with positron emission tomography, right, in medicine. The positronium discovery, I'll a little bit about it. I have a positronium beam too, right, too, or you're developing positronium, right, facility. Then I'll talk about the different technique in positron, and this is very much how it's going through the history. So, again, positron annihilation spectroscopy. The word positron annihilation, it means it annihilates. So why? Because it's antimatter. If you know any matter and antimatter, proton, antiproton, positron, electron, when they meet, annihilate. They completely disappear. The particle disappear and you get energy. Positron, again, electron is the most elementary particle. So when we talk about positron electron annihilation, this is a very fundamental, actually, matter-antimatter interaction. So for us, the physicists, there's a lot of interesting physics there. You can study when you study the interaction between electron and positron. Well, I'm showing you some photo here. So the electron positron, as soon as they get close, they completely disappear, and you get 2 511 photon. Are you familiar with this number, 511? 511 is the rest mass energy of the electron. This is 511 kilo electron volts, and then we get exactly 511 2 photon. What's interesting in this is, you're familiar with the Einstein equation, right? E equal mc squared. So I'm always fact when teaches a student in physics, we said them this positron electron annihilation is actually very, it's the best demonstration for Einstein equation E equal mc squared. Why? Because in nuclear reactor, you see a nuclear reaction, you see part of the matter are transferred into energy, right? And you get this amount, huge amount of energy when you multiply the mass times c squared. In fact, in electron positron annihilation, you convert 100% of the mass into the energy. So all of the mass here and convert it to energy. So I always say this is really shows the best demonstration between matter and the energy are the same. And we see the opposite process. We see also we can get from the two photon, we can get electron and positron, what we call the pair production. You generate electron and positron this way. What we have here, hydrogen and anti-hydrogen, there is a big work in CERN lab to generate antimatter as a hydrogen, the anti-hydrogen, and there's a lot of. This is Dirac and the anti-Dirac. This is a joke, of course. Okay, so I don't want to talk. This is again the physics of it. When they annihilate, they can annihilate with positron has energy, and we call this positron annihilation in flight, or they can annihilate when they have no energy, so zero kinetic energy. This time they give exactly 2 photons, and each one has 511 kilo electron volt. So let me look to, this also I have to mention to this. Have you heard about this before, the positronium? This is really the simplest type of matter in the universe. It's not the hydrogen atom. It's the positronium. So the positronium is combination of electron and positron. So you see they are combined here, similar to they have the radius, the same radius of hydrogen atom. So here is the electron positron, and here is the hydrogen atom. If you look to their properties, I said they have the same diameter, but positronium don't live too long because it's gonna annihilate. How much it live? It depends on the spin state. There are some in quantum mechanics, or we call the spin of the particle. The spin can spin up or spin down. So if you have the electron positron here, if they have similar spin, they form also positronium. If they have different spin up and down, they form parapositronium. And the parapositronium live 125 seconds. The orthopositronium live only 142 seconds, 142 nanosecond in vacuum. The para live 125 picosecond only. So this is very much we just want to tell people always about, because this is really the simplest type of atom. It's not the hydrogen atom, but what we call positronium. And it's a very nice system to study, to understand a lot of stuff in quantum electrodynamics and in physics. So the positronium atom. Okay, this is like really how they annihilate together, so I just probably gonna skip this. And it goes how part that people are interested in it, and how positron use to look to the material probability and defect. So when positron enter material, it very much thermalizes. It loses all its energy, and then start to diffuse, and then annihilate with the electron and emitting 2 photons here. Like I told, every photon has 511 kilo electron volt. And we do different measurement. We look to how long is a positron lived. This one spectroscopy we can do, and we can get some idea from this about the electron density function of the material. Or we can look to the energy of the emitted photon, the energy distribution of the photon, or the angular distribution of the photon, and we can really get a lot of important information. I will probably move to show you more work here. So this is why I said we have 3 independent techniques: lifetime measurement, Doppler prodding spectroscopy, or angular correlation of the emitted radiation you can do. So here, for the lifetime, if you look to so this is very much what I'm showing here, the positron wave function. This is the electron density function, and how long does a positron live? It depends on the overlap between them. And very much simply, I can measure how much is a positron live, and from this information, I can get information about the electron density function. This is how we can measure the electron density function. And then from the Doppler prodding. So if you think again about an electron and positron, if you have electron has 0 energy, positron has 0 energy, when they annihilate, the momentum has to be conserved, and the momentum and energy has to be conserved. And to be conserved, they have to annihilate back to back. So they have to emit 2 photons back to back each one has exactly 511 kilo electron volt for conservation of momentum to be right. An positron already loses all its energy before annihilation. So it already doesn't have energy. But what about, or momentum? What about the electron? Electron inside the material has momentum. And this is why we don't get exactly 511 photon, but we get 511 plus or minus, depending on the momentum of the electron. So if the electron moving towards the detector, we get 511 plus. Of the electron moving away from the detector, we get 511 minus. And I can get this. And just by looking to this, I can get the electron momentum distribution in one direction of this. Why is this important? I mean, all the probability of material is based on the electron state. It really depends on the electron momentum of this electron. So for us to really understand the the probability of the material, it's important for us to look to this. So this is a way we can measure by the energy. From measuring the energy of the annihilation radiation, we can get this idea. If we do this is what I probably explained it already before I show you this. Before I show you this, that the 511 photon is Doppler shifted, but the longitudinal component of the electron. And this is what I measure by doing here. If you visit the nuclear reactor facility and see the positron beams they have, so they have this detector. You're going to see the detector here, which is measures the 511 photon, the energy of the 511 photon, and you can get this energy distribution. From it, you can get the momentum distribution of electron in one direction. Then if you look to the transverse component of the electron, what they lead to the photon emission and in the XY direction. So very much is the electron momentum. Instead, if you get two electrons exactly 180 degree back to back, you get plus or minus it based on the transverse momentum of the electron. And from this, you can measure the electron momentum in the X direction and in the Y direction. And people in the past have combined the Doppler Broadening measurement and what we call here the angular radiation, the angular correlation of the annihilation radiation. They call it ACAR. They combine this and were able to determine the full electron momentum distribution of the electron, or what we call Fermi surface. You hear about this word? I mean, a physicist like this very much. It's very important for us to really understand any metal or semiconductor or oxide. We look to the electronic structure and the Fermi surface of this material. How we measure this stuff? We measure one of them, of course, is the positron annihilation spectroscopy. So this is an introduction to tell you how positron has been used to determine the electronic structure of material. And up to now, if we develop new nanomaterial or something, we can apply positron annihilation to do this kind of studies. Okay, now I'm going to talk about the important part of now people use positron is to look to defect. For you look to defect in irradiated material, right? You're always very important for you. You want to understand defect because defect and damage for material. And it's something bad, right? You really want to avoid this. But this is not all the story of defect. In fact, for us, people who work in physics and material science, defect is also very important. But it's not the bad part. It is the interesting part for us. So defect really for us is important to manipulate the material probabilities. So, and I'm always give my students this because my students, when they start, I told them, you're going to study defect. Sometimes I said, oh, just a defect. A defect is important. This is what determines the electronic probabilities of material. So let me give you some example here. This is gallium phosphide. It's a semiconductor material. This is how it looks. It's transparent, and it looks this color. It doesn't have any defect. Here, we created vacancies in the material. How much we created? 0.001%. So in every 100,000 atom are created vacancy. You see what happened to material? It's become opaque. The optical probability of the material completely change. This is another semiconductor material important here, zinc oxide. And we grow this stuff in our lab. You see, this is zinc oxide, single crystal. It's transparent material. we annihilate here in zinc vapor. We create oxygen vacancy in it. It's become red, and the electric conductivity become very conductive. We increase the conductivity several times higher than the original conductivity. Why I'm telling you, because always when I introduce this to my students, I tell them, so this is really to understand how defect is important for people who work in the area of semiconductor and electronic or photonic, because we use defect to manipulate the material to create interesting phenomena. So this is really how defect is important, not only for damage stuff, but in general. Okay, so why positron? How positron get to look to defect? And I also want to show that it's unique technique in that sense. So positron here, assume we have a positron from radioactive source or from beam, wherever you get it. It enters the material. It always thermalizes very fast because the annihilation in flight the cross-section is very low, but the thermalization process is high. So it thermalizes very fast and loses all its energy. And then what it does, it starts to diffuse as a particle without energy inside the material. As soon as I find a vacancy or any opening, even smaller than the atom, it gets trapped there. And why is this? You understand why? Because positron is a charged particle. All the nuclei here is also charged particle. So the nuclei charged particle, the positron is charged particle, so there is a repulsive force, right? They try to be away. So the positron try to be away from the nuclei, which is the positive charge. So it really never come closer. It always goes through this opening area in the crystal. But this area, it doesn't have the charged particle. So it forms a minimum potential for positron. Everywhere else, there is repulsive force. It makes the positron to stay away. But this one attracts the positron here trapped. This is really how positron can look to very, very small vacancy, single atom missing. Or it can, even if you have like some less than single atom, some opening between the plane or something, positron can probe this. The diffusion length of positron is very long. This is really very long compared to other particles. It's 100 nanometer. What does that mean? In 100 nanometer, you can probe about 10 to the 7 atom. So if he finds one atom missing in 10 to the 7 atom, it can get trapped here, and it trapped until annihilate. So we talk about here probe with a sensitivity 10 to the minus 7, and that can measure defect or vacancies in terms of atomic size. There is no other technique can do this. So high resolution transmission electron microscopy, they cannot see this kind of defect, and they don't have this kind of resolution. This is really why we consider positron annihilation spectroscopy is a very, very important and effective probe to look to this kind of stuff. Oh, this is here probably, this is always, I don't know if it's going to interest you to look here, but if you study quantum mechanics and you know this is the positron wave function in a block state, when it's in the bulk material without any effect, we call it block state. Here, if the positron get trapped in a vacancy, this is the positron wave function looks like this. It's not spread in the material. So what happens when the positron get trapped? It annihilates, and we see this trapping. We see characteristic changes in the positron annihilation parameter we measure. And this is how we can really know what we have, what kind of defect we have. So here, for example, in Doppler spectroscopy, when I told you, Doppler spectroscopy very much, we measure the 511 peak. And we can see that the peak of the 511, the energy, we measure the energy of the 511, the annihilation radiations of 511, we have to do high energy resolution measurement. We have to use very, very high energy resolution detector, like high purity germanium detectors. Probably people are familiar with this here. And we use this kind of stuff. So the peak of the 511 is Doppler prodding by the electron momentum. But if you get the electron trapped in a peak here, if you get the electron trapped in a vacancy, what happened? It's going to annihilate mainly with the valence electron, because it's only sees the valence electron here. It doesn't see the core electron. You know the difference between the valence electron and core electron? Valence electron has lower momentum. So you get the narrow peak, the 511 peak, it's become narrow. And very much we can measure what we call from the 511 peak. We can measure here, you see the peak here become narrow if I have defect. Now here's Doppler broadening, this Doppler recording become less. And very much I can measure the ratio of positron annihilation was valence electron compared to the ratio annihilation with core electron, and I can use this to give me an idea about how much is the defect increase by doing this. And of course we can do it also this if we do angular deviation. This is not common technique. People don't use it too much for this specific to look to defect. Why? Because it's a very expensive technique. It needs lab, very, very, very large lab to do this. So people always do Doppler broadening and lifetime. So this is very much, I said, how we can calculate the annihilation with valence electron, the annihilation with core electron. Let me move to this one, which is the lifetime spectroscopy. So when the positron get trapped in the vacancy, what's going to happen? In the vacancy, it's very much has low electrolytes. There is no material there. So there is an electron surrounding it, but the electron density in this area much less. So what they expect for the positron? It's going to live longer. So positron in most material, for example, in most metal and semiconductor, it means about 100 picosecond, 200 picosecond. This is the life, the positron live. But if I get trapped in this defect, it's going to live longer because of the lack of the electron here, of the electron density become less, so it's going to live longer. So if you look here, what we can do, we can measure this. Much we measure exactly how the positron, it should be very high timing resolution because we're interested to measure something in few hundred picosecond. So we measure this, and from this curve, we can see the decay constant. We can share how much is the positron live. And the lifetime is related to the size of defect. So I can determine from this measurement if I have single vacancy, if I have double vacancy, if I have cluster, if I have dislocation. And from the intensity of this component, it's also related to the intensity of this kind of defect. So if you look here, what we have, this is silicon, for example. As a bulk, silicon without defect, we only measure one lifetime component with the bulk. But if you have silicon with defect, diavacancy, vacancy cluster, we measure 3 components. And from the lifetime here, we can determine what kind of defect. And from the intensity of the component, we can determine the concentration of defect. So this is why we consider especially lifetime is really important, because it can tell us this information. Something also we can do with positron, people are not really very familiar with this, but this is some of the important stuff for positron. And how can we measure the chemical identity around the defect? Do you know what surrounding is the vacancy, or if you have atom trapped, like some impurity in this vacancy? Can we measure this? In this case, we do coincident Doppler broadening. So we measure the 511 peak by 2 detectors, like this. So instead, in single detector, you get, this is a 511. You see high background radiation. But if I use 2 detectors, I can get very clean spectrum here. So you see, this is very clean. The background become very low, almost I improve it 10 to the 5, the factor. Why is this important for us? Because in this part, I can see positron annihilation with core electron. So we can show here this is what we call the electron momentum and the ratio curve, each one of these corresponding to certain element. Why? The difference between valence electron and core electron in material, valence electron, they are affected by the crystal field in general. But core electron, they are actually they retain the chemical identity of the element. So they are not affected. So when positron annihilate with a core electron, I can know what kind of element surrounding the defect. I don't care about impurity general material like other technique. I am actually probing especially the impurities inside the vacancy or the surrounding the vacancy. And this is, of course, has, you probably, people who work in nuclear material, they know this is really quite important, right, to understand the material and their behavior. Okay, so this is very much what the positron, I hope you get some idea how positron work in terms of looking to defect. The positron source available, we can get radioactive source. There are many radioactive sources we can get positron, but they give positron with a wide energy range. Other thing, we can generate positron from pair production. It's the opposite process for positron annihilation. Positron annihilation, you have electron, two particles, they annihilate. Pair production, you have the electron positron. They actually, and you have a gamma rays with high energy above 1.02 MeV. What happened for this high energy? It can give two particles. It can give electron and positron. And this is the way how you generate electron. How you get this high energy? You get this high energy from electron accelerator, or you get it from neutron reactor, like what you do downstairs here. You have like a neutron beam, and you have a cadmium source. It gives you the high energy gamma ray, and then through the pair production process, you get the electron and positron, and you get the positron from it.
So the sodium 22 is naturally a positron emitter.
Yes.
For the copper 64, you have to irradiate it in order to get the positron.
In fact, the neutron, also the sodium 22, they prepare it also in spallation sources too.
Exactly, you have to do it this way.
Yeah, but they prepare it, for example, for sodium 22, they do it in spallation source, but they give us radioactive for with half-life 2.7 years.
2.7 years.
Yeah, so we can use it for this sense. The copper 64, it's actually very short. So they use it for us for hours, actually, to do so this. And the same stuff they use for positron emission tomography. It has to be very short lifetime, yeah. So this is the kind of stuff. So how we get positron. Of course, it's always with the issue. I talked about positron, by the way, as a positron spectroscopy for defect. Positron could be very, very nice tool if we do all of the stuff we do with electron, like electron diffraction. Positron microscopy. It's really positron is going to be more clean. Why this stuff is not common? Because positron is antimatter. It's hard to keep it. It's harder to have it. So having always how much positron we can get in the wallet so far, maximum 10 to the 8, 10 to the 9 per second to get P. If we get more than this, we can do a lot of nice stuff, a lot of interesting science that actually better than we're doing with electron as a particle. So anyway, this is a conventional method. I talk about the source. So if I use the source right away, I can only do bulk measurement. Why beam bulk measurement? You have bulky material, and you have beam going through this bulk. So you give the idea about the material as a bulk. Because the positron coming from the source, they always have energy like this. So for example, sodium 22, you see how wide of energy. So I cannot measure, I'm going to measure the entire thickness of the material. So like several micron. But if I want to do depth resolved measurement, I want to look to thin film or surface, I have to make a positron beam. So we have to moderate the positron and then start to accelerate them to certain energy. And this is what you have, guys, here. You have a positron beam that you can really look to the certain area, certain depths in the material. So this has been, I think, in probably 1980. And Kelvin Lane, by the way, who one of the people who developed this technique to develop positron beam to do depth resolved measurement, which monitoring of defect as a function of depth, or for people like us who work in thin film and interface. We need a beam. We cannot use bulk material. When you do ion radiation, also you need beam. You cannot use just a bulk measurement. This is one of them. Just we mentioned to this because this is actually one of the. This is the technique I started it and I invented at the beginning of my career, which is instead of using positron beam, positron source like sodium 22 or pair production, what we actually were doing here, instead of doing this, I just use gamma ray directly and don't generate any positron, and I just expose the material to gamma ray, and I use positron annihilation. So all the process, it happens inside the material, and we call this gamma-induced positron spectroscopy. Why this is important technique for us? Because we don't have to go through all the hassle to generate the positron or to deal with radioactive material. All I have the gamma ray, and then expose the material to it, and then I can do lifetime or Doppler spectroscopy. Of course, there's several techniques. We use several accelerators to be able to do this stuff. But also interesting in something, because gamma ray is very penetrating, so you can go to very high depths. With positron beam, you're also limited to very thin layer, 1 micron. Even with positron from the source, you're limited to several micron. But if you want to really probe something like centimeter or millimeter stuff, we don't have a technique for this. And even all the method you use, that X-ray or electron microscopy, all of the stuff for very thin material. So if you want a technique for very thick material, what's our option? Ultrasonic, this stuff. But they are not sensitive. They're actually they become sensitive after you get crack in the material. So if we develop positron, which is the high sensitivity unit, to be able to look to very thick material, this is kind of interesting technique. So in fact, I developed this technique in Idaho, and I've been using it, but then I left Idaho, and it's never been, but German people actually took it, and they developed very nice facility on their superconducting accelerator. So they have this facility now in Germany, and we go to Germany to use it. So this is some of the actually nice idea when I talk how we can make new technique for positron. Other thing also, yeah.
About the accelerator thing, so we're talking here about a Van de Graaff, and I wonder if you were using a vertical or a horizontal Van de Graaff.
I've been using horizontal Van de Graaff.
Is it cascade or just single?
Just a single one.
Single, okay.
And actually, this was very old Van de Graaff, 50 years old. They have it. It worked very well, and it's kind of the stuff. I always look if there is a Van de Graaff accelerator, because this is something easy to do.
Yes.
And if you have some are actually kind of neat measurement, nice to do if you have Van de Graaff accelerator available. Also, the stuff because with the electron accelerator, you can get you can get very short pulse electron beam. There is a pulsed accelerator with around here. For example, this one we use with a nanosecond. This is with an Idaho also, the accelerator center, which is part of INL. So we have like a series MeV electron with a nanosecond pulse. So what actually we did in this work, we synchronize laser pulses with 10 nanosecond with the gamma ray coming from the accelerator. All we did, we converted the electron to gamma ray, and then the gamma ray hits the material to generate positron, and we synchronize the laser at the same time, and then we can look to the electron state during laser excitation. So excite the electron state. So the kind of neat stuff. This stuff is really, we did some preliminary stuff, but it's not really yet. It's not really in the field yet. So, but this is the area we would like it to take positron field to investigate. Okay, the other area I want to investigate, this is kind of nice because we already get this grant. So we're trying to build in situ positron beam and to measure the defect during ion radiation and during corrosion. And at the same time, of course, Jamal he's doing the TEM during ion radiation and the corrosion. So he's doing this part in situ, this part, and doing in situ positron. And of course, we're lucky because DOE liked this proposal and they give us money to develop this. So what we're doing now, actually, we develop beam, positron beam. We're going to have to do pulsed beam to be able to do lifetime, but we do it in situ during the ion radiation. And why it's interesting in this? Because even when we do positron after the measurement, so if you create defect and then you do measurement after this, you really look to the overall of the damage. But for people to understand the damage mechanism, how is the mechanism happen? You really want to look to single cascade, individual cascade. So when you start the irradiation process itself, you started to create defect. If you look to the individual cascade before they overlap, you start to understand how is the defect formation happen, and then how it accumulate. There is a lot of theory, and you have the rate equation, you have a lot of molecular dynamic. They tell you a lot of stuff. This stuff is not tested. It's not tested. Why? Because we don't have a way to look to at the beginning of how is the cascade form, and then how overlap after this. So when we develop this, we want to be able to measure at the very beginning when we started to form as a defect, and then we look how it looks as a defect, how they form it, how much a vacancy, how they lose the vacancy, how they form it after this. So I think this is really going to be important. We say, why is this important for irradiation and the nuclear material and fission reactor and fusion reactor? Because this is going to test a lot of the stuff which is people use to predict the damage in many of this stuff. All right. So this is very much the stuff we propose. So I think I give you enough idea about, I don't know how much time I have. Okay, I still have 15 minutes. Okay, so let me actually switch it to another topic, because this is Farah was talking about positron and how we use positron to look to defect. I want to go look to a little bit different area, which is not positron, but this is development of radiation detector. And the stuff also we look to here, we try to develop scintillation detector. And some part of it, you do this material, and this also material affected by defect. How you get, are you familiar, guys, the students especially, are you familiar with scintillation detector? How it works? Everybody's familiar with scintillation detector? You have a material, right? You get the ionizing radiation, create electron hole pairs. Electron hole pairs, they transfer their energy to luminescence centers. Luminescence center give you light. You connect this scintillation material to photomultiplier tube, and of course you get the electron, you multiply them, and then you get the signal. This is very much the scintillation detector. You have the sodium iodine detector. You have the barium fluoride detector. This kind of detector. There's also many detectors. Cesium iodine. Scintillation. This is a detector are common. Sodium iodide is very common, of course, in nuclear technology. So I want to talk about the specific, what kind of, because we developed some instrumentation that is really very useful in terms of scintillation development. Because what so often people do, how you really develop to develop the scintillation detector, you need to develop first the material here, your scintillation crystal, and then you're gonna connect it to photomultiplier tube. But so the part here, how you develop this part? So most of the measurement people do to test this material is a photoluminescence measurement. They want to know the material to be a scintillation, they have to emit photon, right? So most of the people measurement, they do actually photoluminescence measurement. All they firm is a detector. The student involved here, you make some detector, right, by yourself. And then you can test the detector as for example, in gamma ray or as a particle, you see how it works. But you have to do the detector first. So we developed actually system, we call it X-ray induced luminescence, to measure the scintillation probability of the crystal itself before we make the scintillation. And why this is important? Because this is really what's important for us. You want the material to be good luminescence emitter. So we expose it to X-ray, which is ionizing radiation. It's, as I said here, it's going to generate. When you expose it to X-ray, it's going to generate here electron and hole pairs. And the electron hole pairs, they transfer their energy to luminescent center and you get emission. So how we do this? We have X-ray and then we actually build some spectroscopy here to look to the light emitted. So we have some, I don't know if you're familiar with some optics, you get very much diffraction grating and the CCG, and we have a lens to collect the light, and we connect them to the diffraction grating and CCG. And we cover range from 200 nanometer to 800 nanometer to look to luminescence in this material. And then we actually look to that, use X-ray to look to this. So why is this interesting? Because opposite to light, if I use light, which is the common, people use always photoluminescence to understand the luminescence probability of material. But if you do this, you have to know the excitation wavelengths. So people always has to scan to different wavelengths to be able to show where is the luminescence is. But with the X-ray, because it actually generates a lot of electrons hole with many energy, so we can really detect any luminescent center of the material. So we study by this technique. Let me show you here an example in zinc oxide, for example, when we published this paper in Natural Luminescence literature, actually scientific report. And you can see here, if we do 325 nanometer, we get this emission from zinc oxide. If we do 390 light excitation, we get this. But when I do X-ray, I get the two together. And I can really look to them. And if one from defect versus from the one recombination of electron and hole, I can really see which one I have value. So it really gave me very powerful tool to study this. So when we developed actually this system, we went and to measure some of the important material like YAG. Yttrium aluminum garnet is important material. And people always has, it's a study, it's actually thousands of paper, because this is, they call it the most important optical material because it's the host for laser, the GM-YAG. And then we discovered some luminescence people never reported before, because they really never able to see. For the X-ray excitation, we were able to see this. So we developed these two for a lot of, we actually have, I get patent for this one, and we hope to get it to the market now as a system, as a X-ray induced luminescent spectroscopy. And also we can also control the resolution. We can get good spatial resolution, because X-ray, you can make it very small. You can collimate the X-ray and make it very small. It's not the common for photoluminescence measurement. You always have a high PM, so you can't have good spatial resolution. The important part, yes?
Collimator size.
What's what?
What's the collimator size?
Oh, the collimator size. It was actually, this one was about micron, several micron.
Several micron.
Yeah. And I've been using, so the way actually I developed this, I get all the X-ray machine. It's all the X-ray machine using for X-ray diffraction, but I get the part with the monochromator, monochromator, and with the collimator, and I use them, and then I use there to do the luminescence measure.
So you put the monochromator in front of the X-ray source, and then
Yes.
collimator.
You have the monochromator first, because this, this X-ray machine, they have the monochromator, and then they have the collimator, which is, you can really collimator beam to micron size.
Because you mentioned about the very high spatial resolution, so that's why I'm wondering what kind of collimator you are using in this, like, because
You know the X-ray, when you do X-ray diffraction, the system use X-ray diffraction, and you do like a full X-ray to look to the spectrum. So we use this kind of collimator in the X-ray diffraction.
the same kind of collimator in the, like what you saw in the X-ray diffraction?
Yes, the same one you use for X-ray diffraction. I didn't change it. So I'm saying we use the same X-ray diffraction system, and then we use it for this. But one of the issues that you can really use it this is very small compared to what we do with light.
Because as far as I understand, like when you go to a few micron, so basically your final spatial resolution will be larger than that. So
Yeah, the larger than few micron, right?
Yeah, your final spatial resolution. That's fast.
Yeah, I mean, but this is, if you compare this, if you really compare of this, we talk about 10 micron, several tens of micron. This is very, very, very good resolution compared to what we have in luminescence spectrometer. And you really can compare this. I example you, I didn't actually invent it. I didn't get specific collimator. All I do, I use a collimator which is used for X-ray machine, which is very small compared to the light we use for that. For light, we always have to use a big light. So anyway.
Quickly, what kind of X-ray target here? Is it molybdenum or tungsten?
The molybdenum X-ray,
So
yeah.
22, at energy, what energy?
Oh, at the energy 20, yes, probably 22, I guess, yeah. But the X-ray tube, you can change it. We can use any source here.
Is it one that's the target is replaceable?
Yeah, I mean the tube itself, we can replaceable, yeah. Yeah, you can go to higher one. So let me actually show you here what's really interesting, especially regarding the scintillation, because I said this is important for the scintillation properties of the material. So you can see here when we change the X-ray current, so we change here the power from 100 watt to 170 watt. You can see here we can really change the emission, and then we can integrate the intensity, and you can see the luminescent intensity versus the X-ray power. And what's interesting here, because if it gives me linear, this means this material could work for me, good material as a scintillation detector, because it has linear response to the effect of X-ray. So if I increase X-ray power, or if I increase X-ray current, as very much you see this is linear. So this is really good. It tells me a really important thing about the linearity of the scintillation material developed. So this is some stuff really you cannot do by the stuff that it does exist anyway. So anyway, let me mention what kind of also, so we've been working in this process, and we developed, these people didn't hear about this detector because we call it yttrium aluminum garnet. I guess again is an important material. There is a lot of effort to develop cerium YAG as an efficient scintillator, because cerium YAG is a very, very, very high efficient material. It's actually, when you get the cerium YAG, this is the phosphor. They put it on the, if you have UV sources, they put cerium YAG is the yellow phosphor, where when you get the green emission. So it's a very, very efficient, this. But it's hard to work as a scintillator because of defect on it, and defect it traps the exciton, and you don't get good emission. So we've been working on this, but then we found that the undoped YAG has really some interesting properties. So barium fluoride, for example, we're studying this by this spectrometer we developed, X-ray induced luminescence. And here's the barium fluoride detector. So the emission you get here around 300 nanometer. And the barium fluoride has one very fast emission, which is people use as a fastest detector. So far, barium fluoride detector and the plastic scintillator is really the fastest detector. So if you want applications that you get high timing resolution, you need this kind of detector. So people have been using the barium fluoride for this. So far, as the fastest known scintillator. So we looked at the undoped YAG, and we found we have this emission similar to the barium fluoride. And you see by different treatment, we are actually able to increase this emission from the material. When we treat the material as different annealing, we're able to increase this. And we also looked to the lifetime of this emission. So we found that in YAG, the lifetime is this 0.2 nanosecond compared to the 0.8 nanosecond in barium fluoride detector. So if you look to this here, then we detector. So very much we constructed the YAG. We connected to the Hamamatsu photomultiplier tube, and we connect also the same barium fluoride to the same Hamamatsu point tube, and we exposed them to gamma ray to see how it works as a scintillation detector. And this is the outcome found measured on the oscilloscope. You can see here is the rise time for the two. So for undoped diag, we have 1.7 nanosecond. For the barium fluoride, we have 2.1 nanosecond. So this is very much the same. I don't want to actually, let me go skip here and show you the energy resolution. This is peak measured by the cerium YAG and by undoped YAG. Let me show you. This is the one that's important for me to show you, because this is peak. This is 662 kilo electron volt peak from cesium source, and we measure this with our new detector, which is the undoped YAG, and we get very good energy resolution for this peak, which is 11%. 11% is very good energy resolution with a very fast detector compared to the barium fluoride. So barium fluoride, actually, the energy resolution of barium fluoride is 17%. But for this one, we show it's 11%, and it's much faster detector. So this is some of the stuff we're working on to develop new scintillation detector for this purpose. We don't really use positron here. The last thing I want to mention, probably when I talk to you, Scott, about what interesting in stuff for using a nuclear reactor. Some of the actually stuff we're doing, we use a nuclear reactor very much to dope semiconductor material. You know, people have been using this in silicon, to dope silicon. But we start to look to oxide. And some of the stuff we did was dope zinc oxide. We want to dope it with copper. And we just, when you do it by the normal way, it's always harder to get the copper to stay in the zinc sublattice. So it's always go to the interstitial places. But if you have the zinc itself, you can transmute the zinc to copper. And this is where we know that you need, of course, thermal neutron to do kind of this stuff. But you can really transmute some of the, here for example, zinc, we're able to make, I didn't show this work because I didn't remember until I talked with you that this is some interesting area for application of nuclear reactor in material science that really used to dope a lot of this interesting oxide. So anyway, this is we saw very nice work actually, and this is big area by the way. We published the first paper in 2011, but several people actually follow this, and they started to do special on dope zinc oxide with copper, and the study was the stuff. So it's important in this area in terms of semiconductor material and how we dope semiconductor material. So anyway, I guess I'm done. So this is a summary. I guess I don't want to. You can read it, and I was just going to give acknowledgement for my student and our funding agency. And simply, I want to tell you, we're hosting actually but I don't know if anybody interested in oxide here. We're hosting the international meeting in zinc oxide in Bowling Green 2020. And it's also zinc oxide are all oxide semiconductors. Probably the area is a little bit far from you, but just want to mention it, and I can tell you here where we're here. We're located here. Thank you for your attention.
Is there a quick question for Professor Selim? We've had a few from the professors, maybe from the students.
Yes.
So, in the first slide, you mentioned working on gallium oxide. Do you grow this in your lab?
Yeah, I do metal organic. You probably, it's a good question because you know how hot gallium oxide area is. Yeah, we grow gallium oxides with metal organic chemical vapor deposition. This is really our main use. It's a very important for higher power transistor. So we have actually project with Air Force. So Air Force sensor directors, they are interested in the gallium oxide for a high power transistor.
So, what is the thickness of that?
We grow actually, we grow up to several micron. The growth rate about one micron per hour, our growth rate for a bit, but this is epitaxial growth. So you really have a single crystal, it's a line. And we do most of the gallium oxide. We do actually gallium oxide and sapphire. We do gallium oxide and gallium oxide. So the big interest in gallium oxide and gallium oxide, it's hometaxial growth. And this is a material that it's taking all the attention in the air now in semiconductor field. So it's probably, you're probably familiar with this.
It's an interesting area.
Yeah, it is. It's actually it's a huge area now. Yeah, for again, because it's wide band gap. You talk about, it's about 5 electron volt. So because it's very wide band gap, so you can really have the breakdown voltage is very high. So you can expose it to very high power, and you have a good transistor that doesn't break down. So of course, for military and Air Force people, it's a very important area.
So let's